Indium antimonide is a crystalline compound made from the elements indium and antimony. It is a narrow-gap semiconductor material from the IIIV group used in infrared detectors, including thermal imaging cameras, FLIR systems, infrared homing missile guidance systems, and in infrared astronomy. The indium antimonide detectors are sensitive between 1 to 5 micrometers wavelengths. Indium antimonide was a very common detector in the old single-detector mechanically scanned thermal imaging systems. Another application is as a terahertz radiation source, as it is a strong photodembra emitter. History: INSB crystals have been grown by slow cooling from liquid melt at least since 1954. Physical properties: INSB has the appearance of dark gray silvery metal pieces of powder with vitreous luster. When subjected to temperatures over 500 degrees Celsius, it melts and decomposes, liberating antimony and antimony oxide vapors. INSB is a narrow-gap semiconductor with an energy band gap of 0.17 electron volts at 300 K and 0.23 electron volts at 80 K. The crystal structure is zinc blende with a 0.648 nanometers lattice constant. Undoped INSB possesses the largest ambient temperature, electron mobility, electron drift velocity, and ballistic length of any known semiconductor, except for carbon nanotubes. Indium antimonide photodiode detectors are photovoltaic, generating electric current when subjected to infrared radiation. INSB's internal quantum efficiency is effectively 100%, but is a function of the thickness, particularly for near-band edge photons. Like all narrow-band gap materials, INSB detectors require periodic recalibrations, increasing the complexity of the imaging system. This added complexity is worthwhile where extreme sensitivity is required, e.g. in long-range military thermal imaging systems. INSB detectors also require cooling, as they have to operate at cryogenic temperatures. Large arrays are available. HGC-DTE and PTSI materials with similar use. A layer of indium antimonide sandwiched between layers of aluminium-indium antimonide can act as a quantum well. In such a heterostructure, INSB Halenspa has recently been shown to exhibit a robust quantum Hall effect. This approach is studied in order to construct very fast transistors. Bipolar transistors operating at frequencies up to 85 GHz were constructed from indium antimonide in the late 1990s. Field effect transistors operating at over 200 GHz have been reported more recently. Some models suggest that terahertz frequencies are achievable with this material. Indium antimonide semiconductor devices are also capable of operating with voltages under 0.5 volts, reducing the power requirements. Growth methods: INSB can be grown by solidifying a melt from the liquid state, or epitaxially by liquid phase epitaxy, hot wall epitaxy, and molecular beam epitaxy. It can also be grown from organometallic compounds by MOVPE. Device applications: thermal image detectors using photodiodes are photoelectromagnetic detectors. Magnetic field sensors using magnetoresistance of the Hall effect. Fast transistors. This is due to the high carrier mobility of INSB.